So tonight's important because this is really where we start to see the separation. And the Europeans don't just launch into new scientific developments that surpass the rest of the world. They take a lot of those scientific developments and we'll see, especially in the 1800s, apply them to military tactics and military weaponry. And that will give them the economic and military power to literally conquer most of the rest of the globe. And again, if you just look at the world map and look at the size of Europe compared to all these places that they'll eventually conquer, it doesn't seem likely that they would be able to do that just with their small land base and their small population. But they will conquer the rest of, literally, almost all of Africa by about the year 1900, most of China, most of Southeast Asia, India, much of the Middle East. I mean, this is worldwide imperialism. And the scientific revolution is what brings the Europeans scientifically up to date and then starts surpassing these other world civilizations. European science and philosophy had been very much cut off at the knees by religious obsessions, particularly the Catholic Church's inquisitions. A lot of philosophers were trained in the church, people like Erasmus that we've already talked about, Martin Luther, and even eventually Copernicus, Galileo, Newton. These are very God-fearing types of people. They often hold religious doctorates, advanced degrees. They had gone to college and studied Scripture, and then went into other pursuits and started writing books that started to complain about the religious enthusiasm as hurting mathematical and scientific developments. So first we're going to talk about how the Europeans start to basically rediscover what a lot of ancient civilizations had already discovered. The ancient Greeks, ancient Egyptians knew a lot about astronomy. And the Europeans, in going into the fall of the Roman Empire and into the Middle Ages, stopped studying a lot of that stuff for various different reasons. So when they start catching up with astronomy again, eventually by the time they get to Isaac Newton in the later 1600s, they will start developing new theories about the universe. And then we'll get into more philosophy of how do we think, what do we think is real, interesting other ideas about where do ideas come from in general. So medieval Europe, the end of medieval Europe, around the 1500s, again, looks like this. This is the general map. And it was dangerous to publish scientific pursuits, to write books on this stuff, if you are criticizing especially Scripture, parts of the Bible. And where astronomy is concerned, there are important parts of the Bible that seem to indicate to the people back then that the earth was the center of the universe. Certain quotes would say things like, God put the earth at the center of creation and the earth never moves. So when people, Copernicus had studied these ideas, Galileo had studied these ideas, when they start writing books and theorizing and really rediscovering a lot of ancient texts that indicate that the earth may not be the center, that the sun may be the center, at least of our solar system, becomes a very dangerous thing because people are arrested and sometimes tortured to see if, in the theory of the torture is that if we torture you and you are a good godly person, if God really wants this idea to come out, then God will protect you from the pain of torture, therefore the torture won't matter. So you won't admit that you were wrong under the power of torture. It's an interesting theory. Again, Copernicus was born in the 1470s, had studied religious theology. In fact, I believe he took a doctorate in it, which is a very high-level degree. And it wasn't until after he finished his college studies that he started studying more astronomy and mathematics. And he started apparently doing that on his own time. He worked for the church in certain times and worked for different governments as an advisor. So he's a highly educated guy. Around 1512, 1513, he brings together a lot of things he had studied over about the past 10 years since he had finished at the university. A lot of his mathematical studies. And he put it in a pamphlet, and he gave it to his friends to basically get feedback from them about, is his ideas on the solar system accurate, or the sun being the center accurate, or does he have good proof, all that kind of stuff. His friends thought it was a work of genius, and they encouraged him to publish it. But he doesn't, because he's very, very afraid of what the church will do to him and what political leaders will do to him if this book gets out. So he holds off on publishing the thing, you can see, for another 30 years. Until he is literally dying. He allows the publication to go forward, sends it to a printer, and reportedly we get this very romantic idea of, he's in great pain on his deathbed, and then someone hands him the first actual printed edition of his book, and all the pain went away, died in peace, and all that kind of stuff. Very nice, kind of happy idea. Probably didn't happen. That's very romantic kind of stuff. But that's the story. That's the legend. What are the main contributions of this work that eventually becomes known as On the Revolutions of the Celestial Spheres? Number one, he proclaimed that the sun is near, if not at the center of the universe, which we would today redefine as the solar system. Says that the celestial motions are uniform, therefore predictable, eternal, and based in circles, which we also today know is not exactly true. But that was his early design. And he states openly that the Earth has three different predictable and consistent motions. Number one, it rotates on its own. It spins. That 24-hour rotation creates our days, and that's why we think we see the sun rise and the sun set. The sun doesn't actually move, it's the moving of the Earth that makes us feel like we're watching the sun move when actually us on this planet are rotating. Which opened a lot of questions. If the Earth is rotating, why don't we all just fly off? So he starts also theorizing that there is a force that pulls everything toward the center of the Earth. And that becomes known as gravity eventually. And he also theorized that each of the planets has its own gravity. And this idea that things get pulled toward the ground, toward the center of the Earth, is what convinced a lot of religious scholars, theologians, that the Earth was the center of the universe and that the Bible was right. Because everything's pulled toward the center. If the sun is the center of the universe, then why aren't we pulled toward the sun? Why aren't we pulled off of Earth and sent that way? But he comes up with the theory that each of the planets has its own gravitational pull. So if you're on one of these other planets, you would be pulled toward the center of that one. Okay, so he says that the annual, or 360-day, 365-day or so, revolution is the Earth going around the sun. That's how long it takes, and that's what creates our years. And our seasons are created because the Earth is tilted. It is not kind of perfectly on an axis. It is tilted slightly. Therefore, as it rotates around the sun, in certain times of the year, certain parts of the Earth are exposed to the sun for longer periods. So you have about half of the Earth gets more sunlight more consistently in the summertime, what we think of as the summertime when it's warm, and the other half experiences wintertime, like in Australia right now, right? It's getting toward the end of winter for them, and largely people below the equator. So he's the one who largely came up with the idea of the tilt in the axis, and that's why we experience these vastly different seasons. Right? At least not Los Angeles, but many people experience vastly different seasons. A lot of people seem to believe that the seasons are created because they think that the Earth gets closer to the sun. That when you get closer, that's when it gets warmer. Not true. In the northern hemisphere, we are actually further from the sun in the summertime, and we are closer in the wintertime. So it all has to do with how long your part of the planet is exposed to sunlight. Okay, so pretty basic stuff, right? But these are revolutionary ideas for Europe back then, which shows you how far science has come since. Copernicus called this the heliocentric system. Copernicus, like most European scholars at that time, used Latin as the educated language because they saw themselves as inheritors of the Roman Empire. The Roman people, for the most part, spoke and wrote in Latin up until a certain point. So they think that the Roman Empire was like the height of human civilization. That was the greatest time ever, so they still write in Latin. So he uses the heliocentric system, and it literally translates to sun-centered system. So you get the definition of all the different planets in a row. And this is directly out of his book. This is one of the drawings in the book. You can see that all the planets are supposed to rotate in a perfect kind of circle. We know that isn't true today, right? Yeah. Today we have the elliptical system where the sun is like way off on one side and the circles go way around and get closer. But he was very much into this idea of the solar system, the universe being perfected. So, they said that circles are perfectly equidistant all the way around. And this convinced him also that God had created everything, because in his mind, this stuff just doesn't happen with all these planets being held with their own gravity and gravity in relation to the sun, all that kinds of stuff. This seemed to convince him and a lot of other even scientific scholars back then that God must exist. That this just doesn't happen. That this has to be created and planned by some kind of higher power. So Copernicus publishes the book and very quickly dies right at the moment of publication, basically. And science goes on further. There's other astronomers, like this guy named Galileo Galilei, who is an Italian. He and many, many other astronomers start taking Copernicus's ideas, which becomes known eventually as the Copernican system, and they test it, like good scientists do. You get a theory out there and you test it according to observable data. Put the theory to the test. And a lot of them were coming up with the idea that Copernicus' system appeared very close to true, correct, and this is where they start kind of messing with the system and trying to discover that the perfect circles aren't the absolute truth. We see some variations, and therefore they try to explain that. So they spend some time doing that, and it takes them quite a while. Galileo is known for being one of the major, you wouldn't want to say inventor of the telescope, but he adapted the telescope to very far sight. Telescopes back in his day, when he gets a hold of them, were kind of like fun things to do at a party. They would, get these little pieces of glass, and they would look at each other from across the room, and the thing's magically bigger, and they're all, wowed by that kind of stuff. And he thought that wasn't just a cool thing to use at a party. He started pointing at the sky and making them increasingly powerful to do better observations and get even clearer data on what he saw in the sky. So he becomes an astronomer in himself. He writes a book called The Assayer in 1623, one of his earlier works, or he's not exactly a very young guy at that point, but it takes years and years to do these kinds of studies. So eventually one of his big statements on philosophy is that philosophy is not something you get from the Bible. Philosophy is not something that you have to learn from another person. Philosophy is learned by doing objective, data-based studies on natural phenomena. So he said anyone can be a philosopher. For him, the most important kind of philosophy-based sciences were mathematics, which tend to be pretty objective. You can't really put your own opinion into 2 + 2 = 4, right? I mean, the numbers have to add up. So he thought, and many other of these philosophers will believe, that mathematics is like the highest level of scientific achievement. So he says that the whole universe is a data system. That if you have a problem or you want to understand a phenomenon, like why do hurricanes happen, that kind of stuff, all you have to do is study it. And study it as objectively as possible, build up a set of data, and start coming up with hypotheses and testing. So we have this giant statement that philosophy is not something you just read in a book, it's something you can go out and do in the world. And the more scientists that go out and do these experiments and they start building up objective ideas about how things are happening, then that will advance human knowledge. And obviously he's very interested in math, just by the quote. He also starts writing some controversial books that especially supported Copernicus's idea. So Galileo was a big supporter of Copernicus going into about the 1620s. And Galileo took Copernicus's ideas and really kind of popularized them. Galileo was good at taking very complex, highly educated theories that most Europeans wouldn't be able to read or understand. I mean, this is high-level stuff. And breaking down the ideas and using analogies that more common people would be able to understand. And we often get those kinds of people in society who understand, say, the Stephen Hawking, Albert Einstein kinds of mathematics, those levels, but also understand that, a person like me who doesn't know much about math, has never studied physics, isn't going to open Einstein's book and understand it, right? So you often get these people who become like middlemen, who take the complex theory and break it down to understandable kinds of levels for the mass population. And Galileo was good at that stuff. One of his books was very much challenging to the church's official idea, the Catholic Church. And they called him to a meeting, basically an Inquisition meeting, where he was labeled a heretic by the Catholic Church. And some of his books are banned. So it becomes illegal under areas that are basically governed and influenced by the church to own those books. So Galileo is threatened with being in prison for publishing that stuff. Right about that time also, the Pope dies. So a new Pope is elected. And because Galileo and this whole astronomy controversy is really brewing in Europe, the Catholic Church chooses a Pope who seemed to understand these ideas, who could really fight back and put forward the Church's position and defend it publicly. So this guy who eventually becomes Pope Urban VIII is actually one of Galileo's longtime friends, another kind of philosopher that Galileo had contact with. So they promote this guy to be Pope, and when he becomes Pope, he goes to Galileo and says, look, I'm not going to persecute you if you write a book that also brings the Catholic Church's ideas on astronomy in and kind of debates them with the cutting-edge, more scientific Copernicus idea. So Galileo says, okay, I can do that. He eventually spits out a book called The Dialogue Concerning the Two Chief World Systems. Obviously, the two chief ones are going to be Copernicus versus the Pope. The book is basically a story of how these three guys are hanging out for like a long weekend. They go to one guy's house and they just kind of hang out and they talk and they eat nice lunches and they go for walks and stuff like that. And the subject of their long-term discussion is which side is right. So there's three main characters. There's one guy that's like a Copernicus character, one guy that's a Pope character, and there's like a middle guy that's kind of a mediator between the two, right? A kind of judge. The problem with the book is that it is very one-sided, to the point where he gave the Pope's kind of character the name Simplicius, which implies simpleton, idiot. So this one comes out, and it just presents the Pope's ideas as kind of trapped in its own logic, not being able to understand Copernicus, and eventually just kind of circular logic. So when the book comes out, the Pope is just enraged. This is the one that they really go after. Galileo is brought back into the Inquisition and is eventually imprisoned. There's rumors of his being tortured. His books are banned. And he's put under house arrest basically till the day he dies. So he's not allowed to publish anything. He goes on for a little while longer. The Catholic Church doesn't admit their mistake in doing that for about 100 years, which the Church tends to do every once in a while with philosophers. So they literally went after Galileo and silenced him after this one came out. So Galileo, I think he lives about another 10 years or so. But his freedom is dramatically restricted. His access to people and his access to writing are very closely watched by the church. So the church, even in the mid-1600s, has a lot of power to silence dissent. That leads us to the next guy carrying the baton, who becomes really the highest level European scientist of his time, and one of the big ones in European history right up to today. His name is Isaac Newton. He's an Englishman. He is born right around the time that Galileo is imprisoned and in his last days. Newton is a mathematical genius, and there's not much doubt of that. Newton is one of these guys who jumps ahead of everyone else in his age group at a young age. Fairly wealthy guy. He gets educated. As most people, rich people, try to get their kids to go to school and learn something. So education back then was very much a game for the rich, and Newton jumped ahead of everybody else. By the time he's in his 20s and 30s, he's already got PhDs. He's already teaching at universities. And he's literally viewed as the kind of boy genius of mathematics throughout London, at least, if not the rest of Britain, and rising as a European star. In his about mid-40s, he publishes a book. The long title is called The Mathematical Principles of Natural Philosophy. That's the English translation version. The Latin translation called it the Principia, the Principles. The Principia Mathematica, the Philosophia Natural, something like that. But it's in Latin, so generally it's called the Principia for short. This is literally about 1,200 pages of mathematical proofs. So if you've ever taken like a geometry class where they say angle ABC is correlative to angle DEF, and therefore the point E is has like the exact same radius as point B, that kind of stuff. Imagine about 1,100 pages of that. Yeah. So only about the first 20 pages or so are readable to the average person. That's where he gives his overall theories, and the rest of the book is just literally the mathematical proofs behind all these theories. The large idea that he proves in this book is the theory of universal gravity. So people understood that gravity existed, that you take something and you throw it up in the air, great experiment, and it falls. People understood that gravity exists, but no one could explain how or why. Not only does he explain how gravity exists and how it operates on Earth, he proves how it operates on the moon, on other planets, and how the other planets operate in relation to the sun. So this is a gigantic leap forward for European mathematics. In order to prove these things, he invents calculus in the book. Yeah. So he is operating on very much a higher level than almost anyone alive at that point. It's estimated that probably only about 20 to 50 people alive in his lifetime could actually read that thing. And I've known one person that actually read the whole thing and claims to understand it. I've had him explain the theory to me several times. I get it for about 5 minutes and it goes away. But that's my lifetime relationship with numbers. The impressive part about the theory of universal gravity is he had to prove it in 1,200 pages, but the mathematical formula is actually very short. It was only something like 10 characters long. It was just a simple kind of fraction. So people were just floored that he was able to do this, and that he was able to present this stuff in such, if you understood geometry, a fairly understandable kind of thing. But the problem is that most people can't read it at that level. So again, the popularizers come out. Especially people like a Frenchman named Voltaire eventually take his ideas, put it into analogies that people can understand, and publish their own books explaining Newton's theory. Another important thing that Newton does in the book is he really raises the bar for the amount of evidence you have to prove a scientific theory. I mean, 1,200 pages of that madness is not madness, but high-level thinking, really challenges other scientists. If you want to prove that you know how a hurricane exists, you better come up with a lot of data, and you can't just have a 5 or 6 page paper. That's not going to fly anymore. But again, an interesting thing is that Newton was a God-fearing type of person, and when at the very end, if you read this General Scholium, which is the last chapter of the book, the kind of overall, this is what I've done, this is why it's important, he says that gravity proves, again, that God exists. Because only God could create something like this. And gravity is helped out, especially as the planets rotate and they move through space. Gravity is helped out by angels who hold the planets up and help them rotate. So you get, even with this high-level, mathematical, scientifically obsessed kind of mind, there's another half to it that is very much accepting God's existence and God's power. So if you read the General Scholium, you have both sides. And to us today, where we tend to see religion on one side and science on the other, and that a lot of people have to kind of make a choice in one or the other, a lot of people today read Newton and see him as kind of confusing. But that is Newton's giant, massive contribution. So he becomes a worldwide celebrity. He gets any job he wants, and he stays in teaching, obviously, for basically the rest of his life. He launches forward to basically dominate English science for the rest of his life. And his theories about gravity and the relation of gravity to planets and whatnot are not overturned, are not kind of surpassed until Albert Einstein in the early 1900s. And that was shocking even back then, that someone would go beyond what Newton had accomplished. So this stuff sticks around for 250 years or so. It's a long, long time. So questions about any of this so far? Astronomy, yeah.
How did the church treat Newton?
Well, they saw it as half and half. That he is very much investing in science, but he was very aware to not go against the church, right? But he's also living in England, in Britain, at a time where you have the Restoration. So you have a monarch who's in place that everyone basically believes is probably Catholic, but he's not supporting the Catholic Church openly. He's doing the Elizabeth thing. So Newton is a fairly protected person by his own government. And he even gets government positions. He becomes like one of the head science advisors to the king. Yeah.
So even though he basically proved gravity, and he then says, "Oh well, there's still God," does that he did that to basically protect himself from the church, so that way?
No, he seems to have really believed it.
Okay.
That's not something that even from the reports on the private conversations he had, he puts out the book and he has to give speeches and talks and take questions on in audiences. This is not a theory that he ever tended to back away from.
Okay.
He seems to have really believed it at its core. Yeah. Other questions? No. Okay. And that's not the only thing he did. I mean, if the Nobel Prize was around in Newton's time, he probably would have won it like 6 or 7 times. I mean, he doesn't just work with gravity. He works with the definition of why we see different colors and different light spectra, and just on and on and on. He does all kinds of different things. So he's one of the kind of great geniuses of the time. You don't have to write all these down, but Newton's work, and especially work on astronomy, was so inspiring to a lot of our scientists. Especially, Newton is symbolic of the idea that if you just study something, you can understand the kind of mechanics behind it, how things operate and relate, and you can advance human knowledge. This was very inspiring to a whole lot of people to go off and do more objective, database scientific studies of all kinds of different topics. So you literally see an explosion in Europe in the late 15 and 1600s. And historians generally call this the European scientific revolution. This is where they start really pushing forward in a way that Europeans hadn't done in at least 1,000 years, maybe more like 1,500 years. This is an intellectual explosion for Europe. So you have all these different, what we would think of today as separate subjects starting to rise up. Human anatomy. Back then they didn't understand why blood is important to survival. They knew that when a person gets stabbed or something that they bleed and they die, but they didn't know why that operated. They didn't know what blood's purpose was. And this book literally says the heart is a big pump. The heart's purpose is to move blood. So they understood that the heart stops, that you don't tend to live very much longer, but they didn't know exactly why that is. So you start getting, especially Boyle's work, the very early attempts at what we today call chemistry, neuroscience, neurology, pathology of the brain, nervous systems, and even beyond Newton, this guy starts publishing stuff on light spectra, why we see different colors and whatnot. And these guys are really all friends, and when they live in the certain times. Royal societies develop, kind of royal councils of advisors, groups that are funded by government to come together and have scientific debates. So you get a Royal Academy of the Sciences that is built by the British government in London, that Newton obviously leads for most of the rest of his life. There's another Académie des Sciences in Paris. So the European major capital cities are even investing in this. And these become centers of debate. And by the 1700s, especially in Paris, the debate gets decentralized to the point where even rich people will just start having their own private parties, inventing a lot of these kind of philosophers in to have debates and whatnot. So it doesn't always have to be government sponsored by the 1700s, but government tends to have the most money through tax revenue. So government has a big hand to play in this kind of stuff also. Okay, now the fun stuff. The origin of ideas. Why do we think what we think? What is the source of our ideas? Do they just pop into our head? Are they put there? Or do we have these ideas from birth? I mean, this is also becomes a big debate over time. And this really gets kick-started by an Englishman who is a kind of career politician, but also a scientific type of thinker on the side. His name is Francis Bacon. And when he's not working within corrupt political circles in the English government trying to get favoritism for himself and whatnot, in his spare time he also writes about science. And he writes a lot of kind of general stuff. He's not a big kind of researcher himself. He just sits around thinking about science and how to do science better. So he's not one of these researchers that's studying gravity or hurricanes or floods or erosion or anything like that. He just kind of reads a lot of this stuff and thinks, what is the weaknesses in a lot of these studies and how can we make it better? So he says his basic idea is the former ideas and old definitions of scientific thought should not hold scientists back from questioning. Because the more you question old ideas, the more you can separate what is false from what is true, and you go with what is true and develop better theories, and therefore you progress human knowledge. So he says the goal, the end of science, is to explain natural phenomena, nature, through an objective system of data collection, analysis, hypothesis, testing. Of course, when you do the test, you collect more data, so this becomes a cyclical system. You start at the beginning, you go to the end, and the end starts at the beginning again. You just keep continuing the process. And eventually, this will become known as the scientific method. And he publishes a book in 1620 called The New Organon, which is basically the kind of new body of ideas that claims a lot of very important things for the development of the scientific method, and shows scientists some pitfalls in their thinking that they should avoid if they're going to do good science. And the New Organon's main pieces are listed here. He calls them the four idols, the four challenges or the four threats, the four things that you have to be really aware of if you want to be a good scientist. And number 1, you get the idols of the tribe. This is his term. He says that the human mind likes to see order in things, likes to put things into a system for easy understanding. The human mind does not deal well with chaos, usually. So it tries putting things in relation to each other in order to understand what may be chaotic events. And there's a real problem for that. If scientists start doing this in their studies, in their research, then the eventual theories they come up with may not be true because they may be looking for connections in their data that might not actually exist. So he says the idol of the tribe is the threat that when your mind is trying to see a connection, you should take a step back and say, maybe that connection doesn't exist. Do another study or try to find another objective way of proving if that connection exists or not. Does that make sense? So he says everybody has this problem in their own mind, or most people have this problem in their mind. Don't want to be an absolutist. So that's a major problem going forward, and he advises scientists to avoid that, be aware of it. He says the next one is basically the same idea. He calls it the idols of the cave, but on the individual level now. That individual people have certain things they enjoy, certain systems that appeal to them, that make sense to them almost automatically. So he says, you as an individual scientist, if you're doing research and you start making connections between something and you see it as like this perfect system and your mind just seems to really enjoy that system exists, that should give you pause. That should, start the warning bells in your observations. Because we as individuals, when we see something we like, we become obsessed with it. And we may start to see that system in places where it doesn't really exist in reality. We may want to see it because we enjoy it or because we become obsessed with it. And there's a kind of strange movie that came out, I don't know, 5, 6, 7 years ago called The Number 23. You've ever seen it? Yeah. Where this guy reads a book where he's just an average person going through his daily job and all that stuff. And he reads this book that the theory of the book is that the number 23 is everywhere around us, that you see 2s and 3s everywhere, and so bring them together, like everything happens in 2s or 3s. So literally the rest of the movie is he starts seeing this number 23 everywhere. And right up to the very, very end when he's kind of sitting in a room and he thinks he may have overcome it, and he looks up at the clock and it's, what was it? I think the clock said like 2:15. So the hands are pointing at 2 and 3 again, so he's like starts losing it again. Yeah. So we can become obsessed, and Bacon warned scientists to, when you're doing research and you start realizing that you may be seeing repetitive systems. May not exist, so you better do more experiments and hopefully get other people to run some kind of experiments to test that theory. Another one is, he calls the idols of the marketplace, which is when humans start talking to each other and start getting involved in conversations and debates. Oftentimes, if you go into a debate believing something and someone else sways you or changes your mind, you can give in to popular pressure. So he says this idea of the marketplace, the idol of the marketplace is someone else tells you that something is true, and if they tell you enough times, that can create a bias in your own mind. And this is especially true with younger people, right? Especially with children who, parents tell them something and they seem to believe that is like the word of God or something. This is absolutely true. And that's one of the shocking things about going through adolescence, when you kind of come to your own awareness and you start questioning what your parents tell you. Sometimes it gets ugly, sometimes it doesn't. But even as we grow into adulthood, a lot of times we still cling to a lot of things we're told as little children as absolutely true, even in light of evidence that may prove that those ideas are not true, just because your parents told you. I mean, there's a lot of things socially that happen that way. And he said to be aware of that. And he says the last one is the idols of the theater, which is basically the power of tradition. Just because something has existed for a long time doesn't make it the best option, or doesn't make it true. So you often get people who are traditionalists who just don't want to see systems changed, just because it had, in their lifetime, always operated in a certain way, and they seem to be afraid of altering anything. And a good example of that is, they changed the baseball playoffs this year. A lot of baseball fans are really pissed off at that. Like, why? Well, it's because that's not the way things are. Well, we can always change things and try to make them better, tweak things. And the same thing with the college football stuff. What was it, like 12, 15 years ago when they came up with the computer system to rank teams? Yep, and I was trying to change it again. So you're seeing it happen right now where people are getting pissed off just because it's changing the system that they're used to. And Bacon said, watch out for that if you're a scientist. Just because something has always been taught as true doesn't make it true. You should still run the experiments. Okay, so you have all these problems that Bacon warns people about. The next philosopher in line, a guy named Descartes, Frenchman, tries to come up with ways of overcoming those idols, of overcoming those challenges and those problems. How can we be more objective? How can we analyze our own thoughts to the point where we can remove those possible pitfalls in scientific study? And his two major kind of treatises, little pamphlet kinds of books, The Discourse on Method and Meditations on First Philosophy. He dies at a fairly early age, early 40s, or early 50s. So he doesn't live a very long time, but he writes some shorter books as a younger guy. And those books become very powerful in his own time even. The eventual system that he came up with he called radical doubt. And because Bacon's idols exist in our own minds and our experiences in society, he said that we have to try to tear all of our knowledge down to very basic foundations. And that's why he calls it radical doubt. We have to start doubting everything that we've believed before. And try to go back to zero and try to rebuild our knowledge through scientific study from that point. And one of his big quotes is, humans assume that the things we touch and see are exactly as we touch and see them. Which means that as I am sitting here, I grab onto this desk. Because I see it and I touch it, I assume that it exists in reality as I see it. That my perception is absolutely accurate. And he says that can be a mistake. So radical doubt is going to get very radical, to the point where he will question everything around you. And he tells you to question everything around you. Are we ready? Moving on? Okay. We'll wait because it's going to get nutty in a second. No, it's going to get a lot nuttier. We're going off the cliff here.
Should we take a break first?
No. We'll get through the nutty part, then we'll go to break so you can consider the nuttiness as you're walking around. And consider the fact you might not actually be walking around. Yeah. Are we ready? Okay, so this is a system of doubt. So he is going to build up step by step what you should doubt. according to your own experiences. So, you have an idea that he says he wants to doubt, and he will give evidence for it. So he says, his idea is that our senses deceive us. Again, the things we see may not actually be as we see them. Right? So he says that the idea that our senses deceive us can be proven by the existence of size and color. So if I'm standing in here and I'm looking out the door and I see a car off in the parking lot, the car appears like that big, right? Is it actually that big? No, because we're far away, our senses deceive us. Does that make sense?
Yeah.
Okay. So he says that anything of any size, we do not know for certain, even if we're standing right next to it. Our senses can still be deceiving us. But he says, even if you're looking around and you doubt the size of all these things around you, the one thing that you know for certain is that you're actually in this room standing here looking at stuff. Does that make sense? Okay. So he says that the power he's talking about is senses, sense perception of the things around you, but you are actually here in this room looking around. Then he says, wait a minute. I've had experiences where I thought I was somewhere else and it turned out I wasn't. Like when I'm dreaming. Sometimes I'm dreaming that I am flying like a bird, nice and happy. Am I actually? No. So our perception that we are actually here in this room might be false. He is doubting that I'm standing right here, that you are here right now. Because you could be in your bed dreaming all this right now. You could be in an insane asylum, in a padded cell with a straitjacket, and all this could be a fantasy. Right? So he's saying that the fact that we are here can be doubted. So the next level he goes to, hardcore mathematical principles. He says, at that level are still beyond doubt. They are still absolutely rigid, completely true. Stuff like 2 + 2 = 4. Can that be doubted? He says yes. What is the only reason that we believe 2 + 2 = 4? Because someone told us, and because every time we do 2 and 2, holy crap, I have 4. Now I'll go over here. 2 and 2, now I have 4. So he says, our consistent experience of mathematics proves to us that mathematics is beyond doubt. But he says there is one instance where every single experience you've ever had could be a lie. And he calls that the demon God. Basically, the devil can be deceiving you every single time you add up 2 and 2. It might be 8. It might be 282. Who knows? If every single time you've run the experiment you have been deceived by some kind of higher power or something like that, then you cannot reliably say, philosophically, that 2 + 2 = 4. He says you have to still, all the way down to that principle, doubt mathematics. So you could be in a padded room with a straitjacket, you could be here. Everything you've experienced up to this point could be a deception. And who is powerful enough to do that? God, the devil, those kinds of very, very large powers that have the power to create everything we see around us and make us feel that it is true. Sound familiar? Seen it in any movies at all? Huh?
Inception.
Inception's one. That's a good recent one.
Matrix.
Matrix is probably a better one. And the Matrix is based off this. Almost completely. But he says that even when you're doubting mathematics, he says, the one thing I cannot doubt is that I exist. I may be in a padded cell, I may be in my bed, I may be out on Jupiter, I may be in some place that we don't even know about in this completely deceived life. But the one thing we know for certain is because we're asking these questions, because we're using this doubt, that we exist in some form somewhere. And his big quote is, I think, therefore I am. The very fact that I am thinking about this proves that I exist somehow, somewhere, some way. So the one thing that cannot, the one major power that we have is reason. Our ability for critical thought. Okay, so let's see. Yeah, we'll keep going with this. All this makes sense still? Okay, so like I said, we're off the cliff now because he says you're doubting everything around you and all of your past experiences. Descartes, in the same works, also said that there are certain ideas that God puts into our brain at birth. He calls these innate ideas. And he's a mathematician for the most part, so he thinks that math is the highest level. So he thinks that math is put into human brains at birth. So he uses the example of 2 + 2 = 4. He says that children understand that from birth. Why? Because everybody accepts it as true. How else could that happen unless God gave it to us? And he gives another example. He says, an object cannot be completely red and completely blue at the same time. It is either red or blue completely, or it is a mix. So he says that that idea is also an example of things that, these innate ideas that God puts in human brains at birth. Or before birth, but we have it immediately. And that sets up the next big philosopher to come along and attack that idea. So Descartes dies around, I think right around the year 1650, right in the middle of the century. So these ideas are circulating about radical doubt even before Newton has come along and published his stuff. So a lot of this stuff is all happening at the same time. It's all being debated. It's all colliding in intellectual circles at the same time. And the next guy who comes along is in the late 1600s, John Locke. Again, Englishman. He very much disputes the innate ideas theory. Locke proposes that there are no ideas in the human brain at birth. He calls the human brain a blank slate, a big blank piece of paper that experience puts knowledge into. So Locke's idea says that humans come to understand 2 + 2 = 4 over time because they're taught it and they see it as a consistent experience. It is always proven true whenever they run the experiment. So he says it's not God putting it into our brains, it's the fact that we've learned it and it seems to be well proven over time, over the many years we've been alive. So he says that people aren't born knowing that 2 + 2 = 4 because you have to teach children what 2, what 4, what plus, and what equals all mean, right? So he says that education is the key. And Locke is big into education. So he says that ideas are learned by experience and the sense perceptions, and education plays a huge role in this and kind of building up a systematic understanding. Locke has what he calls simple ideas, 2 + 2 = 4, that kind of stuff, or 2 is a simple idea, 4 is a simple idea, and when you combine all those terms, you get a complex idea, 2 + 2 = 4. Does that make sense? So he says simple ideas are just kind of what he would say like self-evident, and they just exist as they are. And when you bring a lot of those simple ideas together, they create complexity. And he says that those complex ideas and those simple ideas are just like pictures in our brain. So if I'm looking around and I see that door over there in the corner, and I close my eyes, I can still see the door in my brain, right? I have that memory. So Locke says that the brain just kind of takes pictures of stuff through its senses and stores it in a box in the head. So he says that ideas are just representations. They're just pictures of things that actually exist that get stored in the brain. And he says one of the big problems of education is that people start throwing around a lot of terminology that they don't even understand. People like to use big words that they don't have control over, and that creates a lot of confusion in society. He says that people that just talk and talk and talk and use big words without understanding, or just talk without meaning, he says they talk like birds to each other. Chirp, 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 chirp. He calls it parrot talk, where a lot of people just imitate what they hear without understanding. And he says that causes a lot of confusion and destruction. The bad use of language, or the poor understanding, poor use of language. Which is always interesting to me when I look at that Twitter site when people just kind of, And there's a limit to how much you can write, right? It's like this ridiculously small amount. To the point you cannot explain complex ideas. It just has to be real simple. But people enjoy it for some reason. Okay, so questions about Locke at all? Locke said that he solved the problem that Descartes gave him. This innate ideas, Locke really just went after that and destroyed it. But this idea of representations in the human brain creates a new problem, which is pointed out by a graduate student, a guy named George Berkeley, in his treatise concerning the principles of human understanding. Comes out just a couple decades later. This guy who was studying John Locke's work and understood the major problem. If all ideas are merely representations of perceived objects, then what's the problem? What did Descartes and others point out with radical doubt? What is the problem of perception?
Can't trust it.
You can't trust it. It might be wrong. So Berkeley comes up again with a kind of radical doubt. If all your memories and all your knowledge is just a representation of outside objects, what happens if the camera taking the picture is flawed? What happens if your vision isn't good? What happens if you're colorblind? You can have big problems. He says there is no way to know the difference between what is real out there in the physical world or the physical universe and your misperception of it. If all your brain is doing is taking pictures of things that your senses perceive, and your camera is flawed, then how do you ever know that the camera is flawed? He says that's the great trap. We are trapped in our own mental box, our own perception of the world. There is no way to know the difference between what is really out there and what we think is out there. So Berkeley's big, it's a lot like Descartes. His big statement is, I pound on this desk. I think I did that. I shoved my hand forward, it stopped, and it hurt, and I hear a bang, and I look at it, and I hear the bang and it hurt right when I see that I think I made contact. But Berkeley says, you may not be doing that. He says that maybe you're actually hitting something else, or you might not be hitting anything at all. You may be having a physical spasm in your hand that is deceiving your brain. That's where the pain comes from. You may be hearing some other noise coming from somewhere else. There is no way to know.
Well, what if someone sees you do it and tells you you're doing it?
They could also be deceived, right? This is radical doubt. It says everything out there that we know of is unreliable. The more testimony you get may make it more likely that it's true, but there's still that little bit of a percentage, right? That everything you see may be false. And that very much worried people. And people in the 1700s went nuts trying to find examples to prove Berkeley wrong. And one famous philosopher, literary figure, published a kind of little story where he says, I'm walking through the forest and I see a stone in the road, and I kick the stone and say, I refute Berkeley thus. And I kick it. And I say, I see I kick it, I feel I kick it, therefore Berkeley's wrong. Which is a really bad example because Berkeley explained in his book, you cannot rely on that stuff. So maybe a person who saw the movie and didn't read the book or something. That's a joke. They didn't have movies back then. But we do now. So a lot of these philosophies are very heavily represented in the Matrix. So we'll go through it. And there's a really good little, I think it's about an hour-long little movie called Philosophy in the Matrix or something like that, where it literally analyzes all these philosophies and goes through step by step in the movie and shows how the movie represents them consciously. The writers created that movie to do it. The movie was just their vehicle to explain it. Okay, so we get, again, the popularizers of science and philosophy. Making movies now. Last one I want to go through real fast is the logical end to the theory of ideas and where they come from. David Hume is one of the later philosophers, lives into the later 1700s, so we've gone a few hundred years in just an hour now of philosophy. And eventually Hume came up with the idea and proposed that what Berkeley and others had written really destroys the ability to proclaim real philosophical objectivity in anything. He says it is impossible. There is no certainty that things are as we see them, or as we even measure them. And that's largely where a lot of scientists still are today. They don't claim to have certainty over things. Scientists back in the 1600s would say we are arriving at absolute truths. Scientists today don't usually say those kinds of things. They usually say things like we are trying to attain greater definitions or more accuracy or something like that, and that it's an ongoing process.